Alright, so the last one is the Cat3 product. So the Cat3 itself, alright, is addition of layer to the surface. So instead of doing certain chemical reaction within the surface region, or we actually change the face of the surface, the martensite, everything, now we talk about additional layer. Alright, thin layer will do. So the examples that you're gonna explain if that happen that they ask is using a vapor depositions method. Alright, so how it works is that you have a certain metal evaporator. So you put in the metal already, and then for certain reason it evaporate all the metals into vapors. It evaporate the metals already and then send it into this chamber. And this chamber over here will be somewhat condensed and condense the vapor of the metal out. Alright, so once it condensed already, is within this region, and therefore some of the metal will actually be deposited onto the surface of this metal. As you can see, it's a deposited metal. So it created a thin layer of surface around this material. Okay, and this material is your substrate. You can put in plastic, ceramic, or even your metal also can. Alright, while the rest of the vapor of the metal will be vacuumed out from over here. Alright, so the rest will be sucked out. Alright, so the wanted deposit metal will create a layers of things onto the metal. Hopefully kind of clear. Take note of the words like low vacuum condition, and normally the process is limited to a very thin coating thickness. Alright, so this process is a bit like chemical reaction, but I don't know why they say it's created like a thin layer, so I don't know. So the deposited materials may include metals or whatever. Alright, the substrates may be metals, blah 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 blah. Typical applications include blah 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 blah. Alright, so there is a blur area between what is creating a layer of protection and the chemical reaction. So yeah, that's the thing. So over here you see the substrate. So this means the piece of our material is having chemical reaction with the gas, which is the vapor. Alright, so there is a chemical reaction, and therefore is chemical reaction to create the layer of the material. Alright, but nonetheless over here all along from our Cat2 we are also doing that, right? We are also doing changing the surface, the chemical surface of the changing the chemical properties of the surface. So I don't know what is the clear fine line between them, such that I don't know. So I'll leave you to think about it. But at least in the exam, if they ask, then you just say that vapor deposition and then explain. Maybe you can draw this diagram. The lecturer never say anything, but in case you may need it, you just check it out. So I think I will also go through this rest of things, but before that I will go to here. Alright, we'll talk about the vapor deposition. Alright, and I think it's the same thing also, nothing much different. So yeah, I think never mind. I'll continue with the rest. So if you want to continue, you can continue, but if you don't want to continue, then goodbye. So you can just check it out now. So what is the weld overlay? So I think as the name suggests, the weld overlay is like welding. So you weld the surface, alright, so that it created a welded surface to protect the layer. Alright, so the welded surface is something like oxide also. So the oxide will protect from the environment. So let's take a look. So as you can see, it's actually welding the surface with a slightly precision. So I think you kind of know what the meaning already. I don't need to. So you can weld for complex geometry. Alright, flexible anti-corrosion method. Alright, so it's good for corrosion. Alright, and it can anti whatever thing that is. Okay, so now is the thermal plasma spray. Let's take a look. So over here, right, if you just take a look, it's dancing with me. So how it works is like you have this spray over here, this plasma spray. So you spray onto this thing, and it kind of create this layer, as you can see, this silver color one, as opposed to this aluminium very shiny color. So it's trying to create a layer, protective layer with this plasma spray. That's all it is. Alright, but trying to know more, alright, and let's take a look on the description video.
The plasma coating process, as the name infers, utilizes ionized gases, bringing them to a state of dissociation. We then harness the resulting heat of this dissociation or plasma using a non-transferred arc method and feeding micron-grade coating stock into the ionized gas stream, melting and propelling the coating material to the workpiece. This intense temperature capability of plasma coating systems makes it particularly ideal for higher melting point material such as ceramic coatings. It should be noted, though, during this high-temperature coating process, the temperature of the component receiving the coating is maintained below 350 degrees Fahrenheit. Hard ceramics like chromium oxide, aluminum oxide, and titanium dioxides are extremely wear-resistant when plasma sprayed. Plasma coatings of yttrium stabilized zirconia and magnesium zirconate display terrific thermal barrier properties, excellent thermal shock resistance, high-temperature corrosion resistance, as well as resistance to the action of molten materials. Plasma coatings make good use of extreme temperatures of ionized gases, making it the perfect process for coating components with high melting points such as ceramic materials. The plasma coating process brings out the most useful properties of ceramic coatings, from very high hardness and wear properties to exceptional thermal barrier and high temperature stability capabilities.
So it's more on the ceramic side, because the ceramic has a high melting temperature. So using this type of coating is actually good for ceramics. Alright, at least you gotta know these things. Alright, so the next one is actually the electroplating, electroless plating. So let's take a look. Wow, a fellow Singaporean. Anyway, so over here, right, this, if you think about it, is actually from Cat 2. Alright, it's anodizing. It's exactly the same thing. I don't know why he put it here. I mean, I don't know why Cat 2 is anodizing while anodizing is not in Cat 3. Yeah, that's why there's a bit weird area, but let's take a look on, at least he will explain better than me. Okay, so let's look at it.
To electroplate this key, okay, let's say this key made out of irons, okay, and irons can rust easily. We want to prevent rusting, so we want to electroplate this key with layers of copper. We want the copper to cover the surface of these irons. So the idea is we use copper metals, okay, the atoms of the copper metals. You take it as the anode, and which one you should take it as the cathodes, anode or cathodes. Okay, so if you want to electroplate a key, okay, so should you put the key at the cathodes or should you put the key at the anode? So which one should be the cathode and which one should be the anode? Now here, okay, obviously, okay, because it's already labeled here, right? Okay, it's already labeled here. So the key is the cathodes, and the metals that we want to electroplate on the key is anodes. But the question is, why the cathode should be the key, but why not? Why not the key is attached to the anode? To answer this, we need to know what will happen during electrolysis. Now during electrolysis, the electrolyte that we use is copper sulfate. The electrolyte that we use is copper sulfate. It's a copper sulfate solutions. Now can any of you tell me what are the ions that are present in copper 2 sulfate solutions? Okay, there are copper ions and sulfate ions, right? Sulfate ions, hydroxide ions, and hydrogen ions, right? Hydrogen ions. Okay. So during electrolysis, the copper ions and the hydrogen ions, it will go to the cathode or anode. Copper ion is positive, so it will go to the cathode. Okay. So these two ions, it will go to the cathodes. Now after these two ions, it go to the cathode. Which one will be selected to be discharged? Copper and hydrogen. Which one will be selected to be discharged? Copper. Because copper is lower than hydrogen in electrochemical series, and therefore copper will be selected to be discharged. So when copper selected to be discharged, the copper ions, it will form copper atom, okay, plus the electrons at the left hand side, okay. So it will form copper atoms, okay. So this is copper atom or copper deposit on the surface of the cathodes. That's why the key must be the cathodes. Okay, the key must be the cathode. If the key is the anode,
I think you roughly get the idea of it lah. Some chemical reaction that occurs that created a surface. Alright, and this explains, I also don't know why anodizing is in Cat 2. Alright, that's a good question. I don't know. So after knowing electroplating, let's talk about polymer coating now. So next up is the polymer coating. Alright, let's take a look and what is it all about. think is the different coating will give you different color. As you can see, there is lighter color and brighter color on the piece, right? So therefore I think it's just showing you the coating itself, just a polymer. A rough coating will do. Alright, and next is the hot dipping. So I think there's a hot dip galvanizing process. Alright, the galvanizing I think is to prevent corrosion if I'm not wrong. But anyway, let's continue. So it's just a series of stuff that's going on. Rinsing, alright, flux solution, and then molten zinc bath inspection. So I think there is no hot dip. Maybe the flux solution is the, I don't know where's the heat coming from, then the name hot. So let's take a look. Okay, so it is actually being submerged in a molten zinc at about 449 degrees Celsius. Alright, so as you can see, there is the molten zinc bath, or at the galvanizing path. I think you kind of find it. Alright, I don't need to draw it up for you. Okay, so the molten zinc bath is the one that is very high dip. Alright, so high temperature, so therefore it's a hot dip galvanizing process. Okay, hopefully you are clear. Not recording anyway, so when exposed to the atmosphere, the pure reaction with the oxygen and these things happens. So as you can see, it's also chemical reaction on the surface. So I don't know why they are talking about additional layer to the surface. That's a weird thing lah. They should be the same, right? The chemical and this one. That's why I don't know what the hell is going on. Alright, but anyway, hot dip now laser alloying. So let's see laser alloying. So this is a laser alloying, and I think this laser alloying also gives us a good understanding of what the hell is going on. Okay, so there will be a pre-coating. So for the layering, alright, for all these layers, additional of layer to the surface, right, we will all have a pre-coating that is existing in there. Alright, so we will first apply a pre-coating in order to conduct a certain experiment. So over here, the laser alloying is using a pre-coating first, and then they use a laser to melt the pre-coating to protect the specimen surface. Alright, so you add in a layer. Okay, and therefore it's different from our laser transformation hardening method. Alright, so instead of transformation hardening, you are talking about transformation hardening onto the pre-coating, the coat, yeah. So therefore, I think this also applies to other methods. Alright, as mentioned. Alright, the other layers. So other layers, I think they also have certain layers pre-done or pre-coat, or the purpose is just to coat around the thing. It doesn't have any much of a chemical reaction as opposed to here. Alright, I think. So there is a very fine line between them. So yeah, and therefore painting, I don't need to explain. Painting is just painting, and yeah lor, I think this is it for surface one. Okay, and therefore we have already cleared away the cat 1, cat 2, cat 3. So see you other video.